answer is C.
It's in the thing.
It's inside. No. Oh, it's up here. Okay, thanks. Okay, yeah, thank you for coming to the talk. So the title of the talk is the low sensitivity functions from unambiguous certificates. This is joint work with Shalov Ben David, who is graduating from MIT this year, and Avishai Tal, who is doing his second year as a postdoc at IES. So it turns out that our work has some applications to the US-Russia relations, but we didn't know. So just to make sure that we're on the same page about what the sensitivity of f is, so we are going to work with Boolean functions. So it doesn't matter. So here it's more comfortable to work with -1, 1 to the n, but you can think of it as 0, 1 to the n as well. So the sensitivity of f is a measure of complexity of the Boolean function. It's the maximum over all input x's of the sensitivity of f at x, where the sensitivity of f at the input x is just simply the number of bits that matter for that input. So if I flip that bit, the value of f changes. You can also think of sensitivity in the graph theoretic setting. So if I give you a Boolean function, you can define a subgraph of the hypercube where you keep an edge if the value of f on the both endpoints of f of the edge are different. So in this way, the sensitivity becomes the maximum degree of this subgraph. Okay. So this is probably the simplest measure of complexity that you can define, but you can define many other measures that we care about them for various reasons. So you can generalize. So instead of flipping one bit, you can allow flipping blocks of bits, and you get the block sensitivity. You can look at various query complexity measures. So the deterministic version, which is the decision tree complexity. You can allow quantum algorithms to query and compute f, and you get the Q of f. You can allow randomized query complexity. We care about the degree of the multilinear polynomial that agrees with f, or the smallest degree real valued polynomial that agrees with f on -1, 1 to the n. And the relations between all these measures have been studied extensively over the past a few decades, and we understand really well how these things are related to each other, as you can see here. So some of these inequalities just follow from the definitions that, for example, just quantum is more powerful than randomness, more powerful than deterministic. And there are some non-trivial inequalities. For example, why is decision tree complexity bounded by block sensitivity cubed, etc. And there's a reason that I don't have sensitivity in this picture yet. And it's because, surprisingly, after many attempts and works, we still don't really understand how sensitivity is related to all these measures. But what we can see from this picture is that if you put all these inequalities together, you understand that all of these things are polynomially related to each other. So, except we don't really know much about sensitivity. So it follows from the definition of sensitivity that sensitivity is bounded from above by block sensitivity, which I won't define it yet because it doesn't really matter. You can pick degree or anything else. And it was conjectured in '94 by Nissan and Mario Zagedi that, in fact, the reverse is true, that the block sensitivity is also bounded by a constant power of sensitivity. In fact, it was conjectured that C is equal to 2. And as we can see from the previous slide, you can replace block sensitivity with your favorite measure, and answering the question remains equivalent. But what do we know so far about the relation of sensitivity with the other things, not so much. As I said, we know block sensitivity bounds upper bound sensitivity. Hans Ulrich Simon in 1984 showed that the number of relevant variables in a sensitivity S function can be bounded by the sensitivity times 4 to the power of sensitivity. This already tells us that all the measures that I mentioned are going to be bounded by that upper bound because all of them are bounded by the number of relevant variables. This was improved by Kenyon and Kutin for block sensitivity with something that's e to the power of S of f. And later this was improved not long ago by Ambinis, Prusis, and Biroch, that the block sensitivity, which is bounded by certificate complexity, this is the minimum number of bits that you need to certify the value of f at an arbitrary x. And they gave a 2 to the s bound. But what do we know from the other way? So how good of a constant c in the sensitivity conjecture can be hoped for? And these kind of works look at trying to construct functions that have gaps, that have the largest gaps possible for this c. So you want obstructions for the sensitivity conjecture. So the best things we knew up to kind of recently is that block sensitivity is omega of quadratic in the sensitivity. So we know the construction of Rubinstein's function, the construction due to Rubinstein from 95 of a family of functions that have block sensitivity that's at least quadratic. So we can't hope for better than quadratic. And for the degree, you can just simply look at the and of ors function. So and of blocks of ors of the same size. And you get a quadratic. So, and in this work, we will be looking at this kind of thing. So we want to construct functions that have big gaps from sensitivity. So we ask, so can we construct superquadratic separations for sensitivity versus any of the measures that you like? And surprisingly, until very recently, we didn't know superquadratic separations for any of these measures. And Avishai et al. In 2016 constructed a family of functions that have decision tree complexity, that is at least sensitivity to the 2.11. In this work, we construct families of functions that separate several of these measures with a superquadratic separation from sensitivity. In particular, we construct a family of functions that have quantum query complexity that is cubic in at least cubic in the sensitivity. And this automatically gives you, because quantum is much more powerful than both deterministic and randomized, so you get a cubic separation for decision tree and randomized as well, which improves the bound of Avishai et al. For the certificate complexity, we give a bound, we give a separation of 2.22. This is also the superquadratic separation that implies a separation for what is called an unambiguous certificate complexity of f, which upper bounds the certificate complexity. So what is cool about the proof is that I can probably make it and tell you the whole proof in less than 10 minutes. So the proof is, it's a black box proof that tells us that if you give me any separation of a one-sided version of unambiguous certificate complexity from any measure, I can plug it into our theorem and I get a superquadratic separation of sensitivity with that measure that you had. For example, if you give me a family of functions that have a 1.001 separation between UC1 and block sensitivity, I can plug it into our simple construction and I get a new family of functions that have a 2.001 separation between sensitivity and block sensitivity. Before I can formally say our theorem, I have to tell you what unambiguous certificate complexity is. So here I just define the one-sided because we won't be working with the two-sided. So the UC1 of f is going to be the smallest k such that you can certify f of x equal to 1 by at most k bits in an unambiguous way. So what do I mean by this? So there's a family of certificates such that whenever f of x is equal to 1, there's exactly one of these certificates that are satisfied by X, and none of the two certificates in the family are consistent. Okay. And our main theorem is the following. So it says that if you pick any measures from this set of all the things that I had on the first slide, if you construct a family of functions that have m of f is omega of uc1 of f to the power 1 plus alpha, you get a new, we can construct a new family of functions that have 2 plus alpha separation from sensitivity for the same measure. Okay? And we get two corollaries to our theorem by just plugging in previous separations. So we use a family of functions constructed by Aronson, Ben David, and Kothari that had a quadratic separation between quantum complexity, quantum query complexity, and the degree, which was later shown that it does admit a quadratic separation with also the UC1 of f. And we plug that into our theorem, and we automatically get what we wanted, the cubic separation. We also can plug in Unambiguous construction of a family of functions that admit a 1.12 separation between UC1 of f and the certificate complexity. But we notice that we can improve the bound of Mika by just sort of optimizing the constants and the weighting schemes that he had, and improve the separation between certificate complexity and UC1 to 1.22. And this immediately tells us the separation between certificate complexity and sensitivity. Okay, so how does the proof work? So the proof is going to involve it's going to have two steps. The first step is going to we call it a desensitization step, which is, given the family of functions f, I will construct a new function f prime that has three properties. So one of the properties it has is that the sensitivity of f on the 0 inputs is at most 1. So whenever the value of f is 0, I can only flip it to a 1 by changing only one of the bits, at most one of the bits. And we do this by not losing much on the UC1. So UC1 of f, the new function, is going to be still at most 3 times the UC1 of the original function. And the way we construct f prime, all the measures that we care about can only increase, so that they can't decrease. And we will see in a second how do we do this. But why is this useful? It's useful because of the following. So we can pick this desensitized function f prime and compose it with something that's hard for several. Oh, I have one. Okay. It's 10 minutes. Okay. Yeah. So for decision tree randomized and certificate complexity, what we do is we compose f prime with OR. And this will what this will do is the point is that the OR function has full complexity in all of these things. So the decision tree complexity is equal to the number of variables, and they all admit a perfect composition theorem. So what you get is an additional multiplicative factor of UC1. And the fact that we had S0 is equal to 1 and UC1 is at most 3 times UC1, you can show that the sensitivity of the new function is still bounded by UC1. So you immediately get the separation. This is really, it's not hard to check. And we need to just do a little bit more for quantum because the OR function is sort of easy for quantum algorithms. Okay, and just the last slide, so there's some limitations. So we can't obtain any better than quadratic bounds for degree and block sensitivity because we actually proved that block sensitivity is bounded by UC1. So you can't just use our Black-Bos theorem to prove super quadratic bounds. Okay, thank you.